Hi, in this video we will learn about the limit of a function as x approaches to a number a. We will provide an intuitive definition and our approach will be very experimental. Like we will try to understand the limit by looking at the table of values or looking at the graph of the function. Okay, I will start with one example. The function 2x plus 1, we know this function. This function is the graph of this function we also know. It is a line, y equals to 2x plus 1. If I draw this line, it will be this is 1, and then this is maybe, this is how it will look like, yes? Well, so far, what we have was that, okay, someone can ask you what is the value of f at x equal to 0? Well, that we know how to deal with. So we just plug in 0 for x in the formula, and we know that the value of the function at 0 is now 1. We can do this thing by looking at the graph of the function. F at 0 means what? Means find a point whose x on the graph of the function whose x coordinate is 0. In other words, where the graph and the y-axis intersect, and then you find the value of the function. That is 1. We already know. Just one plug-in or just check the graph at that point, what is happening. Now, but this is an interesting thing. We are not now interested in this kind of question. Evaluating is something that we already know what to do with. What we are interested in is what is the trend. So study the trend of values of f as x gets close to 0. In other words, we are not interested in just one shot, just get the value of a function at one point. We are interested in how the values of the function acts when the values of x getting closer to 0. For example, here I can choose 1. Well, see that 1, this function has value 3. I'm not interested in the value. I want to change x to another x which is a little bit closer to 0. And I see that the value of the function, well, can be approximately get to 2.5. Well, I get more close to 0. So 2, and as we do repeat this thing, getting closer to 0, you see that the values of the function getting closer and closer to 1. Well, you can also approach from the left side. So when you have -1 here, this will give us negative value, and then as you can see, the values of y getting closer and closer to this value again, which is 1. This is what is called the limit of the function as x approaches to 1. Well, a little bit more systematic way of studying this thing would be I can use a table of values for the function. For example, this one, we take this one. So we will put values of x in the first row, values of f of x in the second row. And well, okay, we are interested in not the value of the function at 0. So I'm not going to just evaluate. I know how to do that. I want to study how values of function f acts as values of the x gets closer and closer to 1. So I will see what would be the values of the function as I choose values of different values of x as they are getting closer and closer to 0. Here 0 0.1, 0 0.01, these are the values of x which shows that while getting closer, approaching to 0. Also, we can have negative side of this. And you see that again, these are getting closer to closer. So this is how we kind of see it in the table. Values of x getting closer to 0. What will happen for the values of y? Well, plug in every value into x and get the value of f at that point. So at 0 0.1, you multiply the x by 2, you get 0 0.2, add 1 to that. So we get 1.2. The value of the function at 0 0.01 is 1.02. Value of the function at 0 0.001 is 1.002. And the value here is 0.02. For the negative part, negative 0.1 times 2 is negative 0.2. Add 1 to that, we get 0.8. Here we get 0.98, 0.998, 0.9998. And well, this is how you see that the values of the function has a nice trend. They are getting closer and closer to 1. This is when we say well, at least experimenting a few things, we can say that this guy needs to have limit limit equal to 1 as x approaches to 0. Well, let me write down an intuitive definition for this limit in general. So intuitive definition. To be able to study the trend of the values of the function around a point, we have to first make sure that the function is defined around that point. So let f be a function defined around a. When we say around, we mean, well, first of all, around doesn't include a itself. We are not interested at x equal to a. What we are interested in that, well, the values of x which are close to a. So we have to be able to draw or to set up a table of values like this for small values or values of x which are close to a. Then while we say that, we say the limit of f as x approaches to a is equal to L number L. Well, this is a long sentence. The limit of f as x approaches to a is equal to L. The way we denote it or we write it is by this very short notation. So as lim of f of x as x approaches to a, this is how this goes, equals to L. So this is the notation we will use if what happens is that we can get the values of f can get arbitrarily close to L when x is sufficiently close to A. So if the values of f can get arbitrarily close to L when x is sufficiently close to A. So we don't have access to values of f. We can only change values of x. As you can see, the upper row is what we change. But what this says is that f can get as close it was, the values of f can get as close as they want to L with the condition that we choose values of x sufficiently close to A. Well, the very precise definition of this needs a little bit higher knowledge of math. But for now, you just see it this way. So we want to see what value of what number the values of f gets closer and closer as we make the values of x close to A. Okay. Let's do an example. Example. Find lim of x squared minus 1 over x minus 1 as x goes to 1 using a table of values. Table of values. Okay, I need to have a table of values, but before I go there, first thing note here is that the function, well, what is the function? In this case is f of x is equal to x squared minus 1 over x minus 1 is not defined at x equal to 1. The function is not defined at 1. Why? Because the denominator, if you plug in 1, the denominator will be 0. And that's no for us. The domain is everywhere but the points which make the denominator 0. But this function, the function is not defined at A, but defined everywhere else. Everywhere else. Meaning that, well, we can make this a table like that. Well, at 0 it's not defined, but to make such a table, we don't need the value of the function at 0, at 1 in this case. We want the values of the function around 1. Okay, so that is one comment. And then let me bring the table of values here. Okay, and here this is going to be x value, x is equal to 1, and well, we just this thing, and then getting closer to 1. How we can do this? Well, this will be 1.01. Let me just do it even better way. This will be 1.1, 1.01, 1.001, and 1.3. Just some numbers that getting closer to 1, and then the other one would be 0.9, 0.99, 0.39, and so on. Well, this is a good point. You can pause the video and try to complete this table for f of x, the values of f of x. Plug in the values there. But what you will see here would be that This one, the value of the function at 1.1 is 2.1. Pause the video, do it, and then find the limit yourself, and then you can check the limit that I found here. The value of the function at 1.01 is 2.01, 2.001, 2.0001. Here would be 1.9, 1.99, 1. And as you can see now that this function, the values of the function getting closer and closer to 2. Yes. Then this says we can write that limit of x squared minus 1 over x as x approaches to 1 is equal to 2. And well, to be honest, this you may say, how did you know the values that fast? This comes from a fact that, note that when x is not equal to 1 means that the expression is defined. I can do this computation. If x is not equal to 1, we have x squared minus 1 over x minus 1. This, you can decompose this as this. X minus 1, and then you can cancel these two, and you see that for all x's which are not equal to 1, the function indeed is x plus 1, and that's why I had the nice quick values of the function. Well, this is what kind of function is this? This is a line equation for line y equals to x plus 1, and if we draw that one as x approaches to 1, by the way, at 1 this function is not defined, so at 1 I have to leave a hole there, so that is at 1 there is no value of the function. So it was supposed to be 2, but is not there. It is not defined. Now if I get values of x closer to 1, you'll see that, well, the values of y will get close and close to 2. Also from this side, you'll see the values of y getting closer and closer to 2. So as x goes to 1, you see the values of function get closer and closer to 2. Well, let us do another example. This is an interesting example. Well, find the limit of absolute value of x over x as x approaches to 0. Again, function absolute value of x over x is not defined at x equal to 0, but if you write absolute value of x over x, remember absolute value of x is a function which is defined piecewise. So if x is bigger than equal to 0, I cannot put 0 here because the function is not defined. Absolute value of x will be just x itself, so you can cancel, you get 1. And if x is less than 0, you get negative x. Absolute value multiplies another negative sign to a negative number to make it positive. You cancel these two, you get negative 1. In other words, the graph of this function is, well, at 0, this function is not defined. For the values of x bigger than 0, so this is bigger than 0 from here on. So we have this value, 0 is not included there. For values of x less than 1, this is constant negative 1. So this is 1, this is negative 1. Now, if we get close to 0 from right, yes, well, no matter what I put on the positive side, the function, the value of the function on the positive side is going to be 1. So this means that not only the values of the function get close to 1 from the when we get closer to 0 from the right, they are actually equal to 1. That's the best option of getting close to 1. But the issue is that, well, when we get closer to 0, we have to go closer to 0 from both sides. When we choose the negative values, the function is negative 1. So the values of the function is negative 1. And that is an issue, because a function or something getting closer to a number, that number should be just one number. We cannot have function closer both to negative 1 and 1 at the same time. Between negative and 1, negative 1 and 1, there is a gap of 2. So the function cannot get closer to any number. So this is an example that the limit absolute value of x over x does not exist, because the values of the function as x approaches to 0 don't get closer to a number, so it does not exist. That's just an example of the limit does not exist. These kind of computations can be done in a little bit general setting. One of the cases that I like to mention here as a fact, I will write it as fact 1. Limit of a constant function, c is a constant, as x approaches to any number you like is equal to the same constant. Why is that so? Because, well, I can use the table of values in this case. So table of values for this guy here, at any point that you like, x equal to a, you can have always a plus 0.1, a plus 0.01, a plus 0.001, a plus 0.0001. At a I don't need. Here I can say a minus 0.1, a minus 0.01, a minus 0.001, a minus 0. This. So these are the values of x getting closer to a. What happens for values of y or values of f of x? Well, values of f of x, function here is the constant c. It means that no matter what you plug in into function, you will get the same constant c all the times. And you see that this is why the function is getting closer to that constant c. Limit of 1 as x approaches to any point is 1. Limit of 2 as x approaches to any point a is 2, and so on. Also, there is another one, fact 2, I will write it. Limit of the function x, f of x equal to x, as x approaches to a, this is equal to a. And this one we can see through the graph of the function easily. Function f of x equals to x has the graph, the straight line. So this is this one. And at point A, the value of the function is a. So that we know. But we are interested in when you get closer to a. So these guys are getting closer and closer to A from both sides. The point is that this function is y equals to x. So it means that exactly the same way that we are approaching to A, the values of y will also approach to A, because x and y are the same things here. So that is why the limit of function f of x equal to x is equal to 1, to A, as x goes to A. Let me finish this video with an important remark that we have been saying all the way, but I need to write it down to put more emphasis on that. Well, the value of the function, the limit of the function, of a function f as x approaches to A, has a priori nothing to do with the value of the function at A. Indeed, as we have seen, the function may not even be defined at that point, defined at A, but the limit may exist when the limit exists as x goes to A. A nice example of this would be, take the function f of x to be x squared, as x is not equal to 0, as when x is equal to 0, this is equal to 2. Well, you can use either the table or the graph. I will use the graph in this case. So this is the function. This is our friend, the parabola, like this. But at 0, you see, this is piecewise defined function. At 0, the function is not given by x squared. So everywhere else is like parabola. At 0, it is given by this point 2. Now, you see that f at 0, well, given by the definition, is 2. However, when we get closer to 0, the function gets closer and closer to 0. And from the negative side, you see, these are the values of y getting closer and closer to 0. That means that limit of the function as x going to 0 is equal to 0. And you see this is obviously not equal to the value of the function at that point. Well, in this video, as you see, we did have a very experimental approach to define the function, the limit of function at point, using the table or the graph of the function, and we did some examples. You have to make sure that you understand all these examples in detail.